Okay, this is a look at Cognity's relationships of velocity, distance, and acceleration. Um, so calculating a car crash. Okay, please watch that video. Pause this one, watch that one. Concept. While working out the solutions of problems in the subtopic, keep in mind the relationship between position, velocity, and acceleration. How the information are given models of the motion of an object. They are only models. Okay. Remember that velocity is the derivative of position, and acceleration is the derivative of velocity. Um, TOK connection. Kinematics is an application of calculus to motion. Can be considered both a description of something and as knowledge in and of itself. For it describes the movement of a particle or body while simultaneously providing new knowledge in the form of speed or location, for example. Knowledge question. Consider other areas of knowledge. Would you consider the scope of other AOKs to be both description and knowledge production? Well, and this could very well be considered natural sciences because it's physics and it's been tested in physics. So, okay, velocity. Few key terms here. Displacement. Displacement is a change in position. So if you walk around the room and end up back in your seat, you have a zero displacement, even though your distance isn't that. They will use S of t here for displacement. That's pretty common. That's what we used in the calculus book as well. D of t is distance. Distance is essentially the absolute value of displacement. V of t is velocity. You can also call that S prime of t or ds dt. You'll also see this notation. With a dot over it is the same as prime. It's just a different, it's non-American notation. Speed, remember, is magnitude of the velocity vector. And we will be doing derivatives with vectors. A little bit, potentially. So, a particle is moving along a straight line with a displacement from initial position, t after set initial position, displacement from the initial position with the particle of t seconds after the start. S of t equals 3t minus t squared meters. What is the initial velocity of the particle? Well, first thing I need to do is get the velocity. So v of t is the derivative of this, which is 3 minus 2t. I plug in 0 for t, v of 0, that's initial velocity, and I get 3. When is the particle at rest? If a particle is at rest, that means its velocity is 0. That gives us t equals 1.5 seconds. How far is the particle from its initial position at rest, when it is at rest? Um, well, I just plug into the original equation. So that's 4.5 minus 2.25. That's 2.25 meters away. What is the speed of the particle 2 seconds after the start? Is the particle moving away from initial position or towards initial position? So v of 2 is going to give me -1. The speed is 1 meter per second away from its initial position because it's negative. Oh wait, is it? Um, Actually, it should be moving back towards. So it's moving backwards, but this is actually towards because initially it's moving 3, and then it's coming back towards you. Um, and I do not believe it would actually have gotten back by 2 seconds. But we could take a look here at the graphing calculator and see what this looks like. So we know the speed is 1 meter per second. We're going to make a graph of the position function, which is 3x minus x squared. At time equals 2, the slope of this position time graph would be the velocity. Which is my negative, oops, well, that's not very straight. The slope of the tangent line here, not a very nice line, but at 2 is going to be -1. It is coming back towards its original position. So it's no longer moving away, it's moving back towards. Once it goes through its initial position, here it looks like 3, it'll start moving away. This part of the graph right here, this is negative time. So this is not a relevant part of the graph. The graph starts right here. I guess I should clear that off. What is the speed of the particle 4 seconds after its start? Okay, now I'm going to do v of 4. Back to, we had v of t equals 3 minus 2t. At 4, v of 4, 3 minus 2 times 4 is -5. And as we saw in the graph, that's moving away. What is the maximum distance of the particle from initial position at t equals 4? That's that's our maximum distance. Distance is an absolute value, 5 meters. When we look at maximums, and I can just go to the graph here, but if I'm looking for a maximum, I have to look at places where the derivative is 0 or the endpoints. The derivative is 0 here at this relative max here, but that's only a distance of 2, maybe 2.25. Oh, it's 2.25. We did find that. But over here at 4, we're at 5 away. We can clearly see. And if you're answering this on an IB exam, you can just draw out the graph to justify your answer. But what they will probably be looking for is that you considered the 1.5 seconds and you chose intentionally for the endpoint. So now we have a particle moving in a straight line from fixed point P of the particle s of t e to the negative t 2t e to the negative t meters. How far is the particle from P initially? The particle is moving along a straight line and its displacement. So we're going to look at s of 0 to find out how far away it is initially. e to the 0 plus 2 times 0, e to the 0. E to the 0 is 1, 2 times 0, it's 1 meter. When is the particle changing direction? Well, that would be when the velocity equals 0. So probably the easiest way to do this is v of t to get the derivative of e to the negative t is e to the negative t times the derivative of the negative t, which is negative 1, so it's negative e to the negative t. Plus, I've now got to use a product rule. 2, derivative of 2t is 2 e to the negative t plus 2t e to the negative t, and its derivative is e to the negative t times it's negative e to the negative t. So my plus changes to a minus. So if I want to know when it's changing direction, want to know when that's 0. And I have no idea how to do that without a calculator. Maybe there's a way to combine it. Maybe. But could factor out an e to the negative t and use a logarithm, maybe. But that seems like a hassle. So we're going to go to our calculator and we're going to graph it. I'm going to clear out my window. I will enter my equation. Negative e to the negative x plus negative x plus 2 e to the negative x minus 2x e to the negative x. So first thing we're going to do is analyze graph 0. We're going to get this 0. Half a second. This looks like it does not get back to the axis, but I need to double check. So I'm going to look at the table. Okay, and these are all getting very, very close to 0, but notice that they stay negative. So the only place, and again, I'm going to sketch this graph if I'm giving an answer. When is the particle changing direction? Half a second. That's a 0.5. How far is the particle from P when it's changing direction? S of 0.5. So I can do that on the calculator. So I'm going to clear some of this out. Because I entered my thing into F1, F1 of 0.5. It's looks like it's at point P. I'm going to verify that the answer key agrees with me, but that appears to be at point P. No. Oh, I know what my problem is. Never mind. I can't do F1. That would be a nice trick, but F1 was the velocity equation. I need to do the S equation. I did not use the right equation. E to the negative 0.5 plus 2 times 0.5 e to the negative 0.5. So that's just 1. This is 2 e to the negative 1/2. So now let's just enter that into my calculator and see what it says. 2 e to the negative 0.5. And 1.21, that is the answer that they got. So very important. That little function notation is a great trick, but it's important that you use the right function. How long does it take for the particle to get closer to P than 1 meter? So I could graph this again, but I need to now graph the original. And I'm going to clear this out so that my graph's a little easier to see. I'm going to hide my table. Now this was e to the negative x plus 2x e to the negative x. So that's my function. I'm just going to make this 1 here. And it starts at 1. It wants to know how long it takes to get back to 1. So I'm going to set the intersection, find the intersection of these two. 1.256 or 1.26 to 3 significant digits. What is the speed of the particle when it is half a meter from P? That's V of 0.5. And I did that before, and that was 0. Describe the motion for T is greater than 0. It moves away for the first about half a second and then starts moving back towards point P. And if I'm, looks like it gets infinitely close, but never reaches P. Wait a second. What did it ask for me? What is the speed of the particle when it is half a meter away from P? Oh, sorry, I did this wrong. When it is half a meter away. Doesn't say what is the speed a half a second. It asks when it is half a meter away. So, what would I have to do? I'd have to go back to my calculator. I'm going to change F2. And I will have to get a new intersection point. 2.477. So now what I'm looking for is V of 2.477. And unfortunately for me, I cleared my V off of the screen. So you find out that that is negative 0.332 if you go back to your V equation, which was, oh, well, I found it. They didn't, they don't have it written out here. I guess you have to find V somewhere in there. They did that by graphing. Well, velocity would equal zero when you have a horizontal tangent. Okay, example three. A particle is moving on along a straight line. Its displacement from fixed point P on the line t seconds is given by this in meters. For what values c greater than zero will there be a time when the particle is at rest? So it's going to be at rest so first thing I need to do would be find the velocity. So looking at this, we're going to need to we're interested in the velocity, because velocity will be at zero when it's at rest. So v of t, actually before we do v of t, we will factor out an e to the negative t. 1 plus ct. Now I'm going to do the velocity, which needs a product rule. So negative e to the negative t, 1 plus ct, and plus the derivative of that whole inside is c, so e to the negative t times c. So I'm going to distribute this negative through to both of those. So I get e to the negative t, negative 1 minus ct plus c e to the negative t. I can factor an e to the negative t out of that, out of these two things. I could distribute that and then factor it out, but I'm just skipping the distributing part. And I'm trying to find when this equals zero. E to the negative t won't equal zero. But this will. So that set of parentheses. So I need to solve it says, for what values will there be a time? Just any time. So I'm going to solve for t. And I get 1 minus c equals negative ct. I divide by negative c. The negative on the bottom can turn it around on top. That's a little nicer. If I set that this will be 0 when c is 1, because that makes my numerator 0. So I've got 1. I know that c has to be larger than 0. And so the question becomes, is there a time when velocity would equal 0? So between 0 and 1, 0 minus 1, so like 0.5 minus 1 over 0.5 is a negative time. That doesn't exist. T between 0 and 1, or no, not t. If c is between 0 and 1, we would get velocity at a negative time. Never. For what values c equals 1? Yes. For c greater than 1, say 1.1 minus 1 over 1.1, no. So if we look at the solution, we can see is only at rest initially. When you're looking for greater value C greater than 1, it is greater than 0 always. So for these values of C, the particle is at rest at some point. So it started out negative. If C is greater than 1, there will be a point because that is positive. So if C is greater than 1, it starts in a negative direction. If C is greater than 1, it ends in a positive. There is a time when it's positive. Time is positive. And we don't know what that time is, but sometime it has to switch from negative to positive. So the answer is C, values of C greater than or equal to 1. It will be at rest at some unknown time. Okay, now we're going to talk about distance traveled. So, the velocity of a water rocket launched vertically t seconds after the launch is given by this. How long does it take for the rocket to get back to the ground? So, I'm actually looking for it's launched from the ground. I'm looking for a displacement of 0. So, I'm going to look at the integral and find when that is 0. So looking at this, I know that my displacement is going to be 0 when it hits the ground. So displacement is the integral of the velocity function. So I get 12t minus 5t squared plus c. My initial height is 0, so the c is 0. So I'm looking for when this equals 0. I'll factor it. It equals 0 at t equals 0 for first factor, or when 12 minus 5t equals 0. And when you solve that for t, you get 2.4 seconds. Because what is the displacement relative to the starting position of the rocket when it hits the ground? It change in position is 0 meters. What is the total distance traveled by the rocket? Well, you could do this on the calculator, and that should work. Or you could figure out its position at halfway, 1.2 seconds, and double it. If you look at their example, they did the halfway, plugged it in, got 7.2 and doubled it. I'm going to do the calculator method to show that method as well. Menu, calculus, numerical. Wait, that's not a numerical integral. Oh yeah, it is. It's 0 to 2.4. So that's when it hits the ground. I almost forgot my bounds. Take the absolute value. And you can use dt for this. Yeah, 14.4. They get the same value, splitting it as you do on the calculator. So that is perfectly valid. Either way works. Both ways are relatively easy. Um, You have to know for the exam, definite integrals, displacement is definite integral, distance is the definite integral of the absolute value, and I wouldn't worry too much about this. Your calculator will do it. Okay, example 2. Find the derivative of this. So we're looking at our derivative. Didn't mean to change tabs. I don't know why I did that. So, derivative of cosine is negative sine pi x squared. I'm going to have to use a chain rule, but I must leave the inside for the chain rule. Now I multiply by the derivative of that inside. Pi x squared is 2 pi x to the first. The velocity of the particle at time t is given by positive version of that, where t is measured in seconds and distance in meters. Show that the particle is at rest at t equals 0. V of 0, 2 pi times 0, doesn't matter what the rest of this is 0. Find the first two times at which the particle changes direction. I definitely want to graph this. I'm going to clear this. Sine pi x, or 2 pi x sine pi x squared. And again, I'm only going to look at the positives. Let's clear this out. No, I want to get out of tab. Two pi x times sine pi x squared. I need to be in radian mode. Darn it. 2 pi x sine pi x squared. Hmm. I need a times here. It doesn't recognize that. Oh boy. So it starts changing direction a lot. I don't like this window at all. So window zoom, window settings. I don't need anything greater than 0. Probably 3 is going to be plenty. So it starts going forward. It changes direction because I'm looking at the velocity graph. When the velocity changes sign, it changes direction. You would want to sketch this graph. But, oh, it changes at 1. Wow. And, oh, that's square root of 2. How lovely. So 1 and square root of 2. You could look by solving these, yes, at the unit circle, but I really liked the graph. It worked very well. Find the displacement of the particle from its initial position. to the position at which it changes direction for the second time. So the displacement. So that is the integral of the velocity function. And you can see that here. There's no way I'm doing that by hand when I have a graphing calculator to do it. So the beautiful thing is I've already got the velocity function in f1 of x. So menu, at S calculus, numerical integral, it is 0, and you do need to write the integral you're taking on the calculator on your sheet. F1 x dx. So I don't need to type it. That's effectively 0. Wait, hold on. I am in radian mode. And they get 0. So what we had was so close to 0, I went with the calculators giving me a round off error. It is find the distance traveled by the particle from its initial position until it changes direction for the second time. Again, they did this way too hard. So the answer we're looking for is 2. So what I'm going to do is I'm going to use the calculator again. I will copy and paste, but I'm going to insert an absolute value here. I guess it's not going to work quite as well as I hoped. And I'm going to put the absolute value around there instead of trying to separate it where it changes directions the first time. And I get a distance of 4. Why did they get a distance of 2? Oh no, it is 4. Okay. So it moves 2 meters forward till it switches directions at 1, and then it moves 2 meters backwards till it switches directions the second time at square root of 2, which is a total of 4 meters. Man, I like my absolute value trick, and it is perfectly valid. You do not need to do this the harder way. I don't recommend it. You don't have time on the exam. This, now you might have to enter v of x or whatever it is, v of t, but this is valid. It shows the work. Do it the easy way. Okay, example 3. The velocity v of a particle at time t is given by this, where time is measured in seconds and distance is measured in meters. Okay, slightly easier. Show that it's at rest at t equals 0. Well, again, v of 0, you're going to get the sine of pi times 0. The sine of 0 equals 0. This is me showing it. I guess 0 squared, but who cares? Find the first 2 times when the particle changes direction. Okay, I'm going to graph it again. Find the displacement of the particle from its initial position at which changes directions for the second time. Find the distance traveled when it does this for the second time. Okay, we're effectively doing the same thing. Did they show it with using? Yeah, now they showed it with graphing and using the calculator. Distance traveled. And again, I would just use the integral. I would use the integral absolute value. So similar question, but they use the calculator. You can do it by hand, but you don't have time on the test, so don't. Just make a habit of using the calculator. Looking at acceleration, we know that acceleration is the derivative of velocity or the second derivative of position. So this one, example one, find the derivative and then find the acceleration. So find the velocity, v of t. I've got to use product rule again. Negative e to the negative t sine t. I did derivative of first times second plus first times derivative of second. Well, this is not going to be terribly pleasant for... Well, let's factor first. Before I do the acceleration, let's factor. I can factor out an e to the negative t, and that gives me a negative sine t and a positive cosine t. So a of t then, e to the negative t, we'll go negative e to the negative t, cosine t minus sine t, plus e to the negative t, positive. Derivative of cosine is negative sine. Derivative of sine is cosine. So now I'm actually going to expand this out and see if anything cancels or can be combined. So I'm distributing on both. My e to the negative t sine t's look like they're going to cancel. Yep. And I'm left with negative 2 e to the negative t cosine t. Let's check that we are correct. Yep. And yes, they liked the factored method. I think that probably was easier. It saved me a couple product rules. Okay, let's look at example two. The acceleration of a particle moving along a straight line is given by there, where the time is measured in seconds and distance in meters. The initial velocity is 2 meters per second. Find the velocity of the particle in terms of t. Integral of cosine t dt equals sine t plus c. Now I'm told that v of 0 equals 2. That's the initial velocity. So there. Sine of 0, which is 0, plus c equals 2. C equals 2. So my velocity function is v of t equals sine t plus 2. They want to see this. They're going to want to see that. That wasn't supposed to be crossed out. That's supposed to be underlined. And they'll want to see this. Find the displacement of the particle in terms of t. Displacement is change in position. So displacement, the c will always be 0, which is great. So now I've got to do this integral. The integral of sine is negative cosine. S of t is then negative cosine t plus 2t. You probably should justify displacement as a change in position, so c is 0. All right. Find the displacement from its initial position in terms of t. I guess c is not one. Oh, c is not one here. This is, so I know that s of 0 has to be 0. My bad here. So 0 has to equal negative cosine of 0 plus 2 times 0 plus c. Cosine of 0 is negative 1. So c has to equal 1. So my final function is that. You got to watch out for it when it's a sine or a cosine. I haven't come across a lot of those, so they got me with tricky one. Okay, example 3, last example. According to the laws of physics, air resistance ignored, the acceleration of a water-launched rocket vertically is approximately constant to that. What height will the rocket reach if the initial velocity is 15 meters per second? So let's start with getting the velocity. Negative 10 dt. So I get negative 10t plus c, and I know that v of 0 equals 15. So 15 equals negative 10 times 0 plus c equals 15. So v of t equals negative 10t plus 15. When a rocket reaches its maximum height, it stops going up, starts going down, so that's 0. So that's t. T is 1.5. So 1.5 seconds it reaches its maximum height. So if I want to know what height it'll reach, I can just do the integral from 0 to 1.5 of my velocity equation. And I'll do this one by hand, it's easy enough, but again, on your test, I'd probably use the calculator. Negative 5t squared plus 15t. Um, so we're assuming it's launched from a height of 0. There'd be a plus c here. S of 0 should equal 0, so c equals 0 on this one. I guess I don't need a plus c with yeah, I started at 0. So I plug in the bounds. Plug in 1.5 for this. And then I subtract, well, I'm just going to move this over, make it neater. So I always do upper bound minus lower bound. Remember this bracket. Minus lower bound is 0. You can get 0 when I plug that in. And how fast to go twice as high? $11.25. To go twice as high, so I'd need to find S of t to be 11.25, and I don't know V0 this time. So instead of this being a 15, I don't know it. So effectively what they've done is they've taken my integral except instead of the 15t, we've got V0t. And what I currently don't know is what my t is. But I do know that S of t is 22.5. Um, and I also know this useful piece of information that at the top, 0 is going to equal V0 minus 10t. So I'm using this at the top, the velocity is 0. So V0 over 10 is going to equal t when I solve. So I can do negative 5 V0 over 10 squared plus V0 times V0 over 10 gives me 22.5 equals negative 5 V0 over 100, V0 squared, plus V0 squared over 10. So if I multiply both sides by 100, I get 2250 equals negative 5 V0 squared plus 10 V0 squared. So here I multiplied everything by 100. That clears both denominators, but it does make the second one 10 V0 squared. When I combine like terms on my right side now, I've got 5 V0 squared equals 2250. So I'll divide both sides by 5. And that equals the 450 they've got right here. So then I end up with 450 equals V0 squared, and V0 equals 21.2. The trick to that was the second equation to plug in for t. And that is the end of 5.13.0 through 5.13.3. I know this was a long one.